Okay, we have another integral today. We've got the integral from 0 to 8 pi of cosine to the 8th x dx. This is kind of a follow-up to my other video, or kind of a two-parter, where the other one I think we had sine to the 7th x and maybe it was just pi over 2. So some of the same ideas, but it's a different scenario with the bounds being different. The sine versus cosine doesn't matter very much, but even power versus odd power, that kind of matters. So again, like the last one, my purpose for this is to compare all the methods, or all the methods I can think of. I don't usually do it this way. I usually like to just do one method and let it be, or sometimes I do multiple methods but in separate videos. Here I really want to compare and try to figure out which way is the best. Okay, so we have over here the 4 methods I came up with. Let me know if you can think of some others. This is pretty much all I had in mind. Other than, there's going to be some variations, like with the complex methods, there's probably multiple ways. With this one, using the Wallis integral, there's probably multiple ways to reduce it, but it doesn't really matter how you do that part. The part where you reduce the balance is very fast, no matter how you do it. So that's not really going to matter. Going through this, starting with method number 1, I'm going to reject this one because, first of all, it's boring. Second of all, it can be really tedious. The other thing about trig identities, it just gets worse and worse with larger powers. Like, yeah, you could do this because you can reduce cosine squared multiple times. But what if that was like cosine to the 12th? What if that was cosine to the 2024? I don't really like this way, so let's just obliterate it altogether. Method number 2, power reduction. This is going to be fast. This with Wallis integral, this is going to be fast. I kind of prefer number 2, but these are really similar, so not too much difference between these here, really. It's just kind of taste, probably. Complex, this is interesting. In the other video where we had sine to the 7th x, I didn't do it with complex method because it seemed like a mess, but here I think it's a lot better. So I don't know if it's as good as these two, but it's interesting. So let's do this. I think let's start with the complex method, and we'll get back to these later. Okay, for the complex method, we'll start with all these definitions over here to the right. We've got our complex definition for cosine right here, but we're going to abbreviate it with z, where z is just going to be the same thing as e to the ix. Got an expression here for 1 over z, turning cosine x into this expression. This is a 2 right here. We have 1/2, and then we've got the z's. And then this is what it looks like when we take this to the 8th power. Now, the part of this that could slow you down is expanding out this, especially when you have more terms, right? Because you're going to want to expand this out with binomial theorem. What's going to happen, it's just going to be your normal thing. It's going to look like you're going to have, for the first term, z to the 8. Then you're going to have like 8 choose 1, z to the 7 times 1 over z. And this is going to go all the way down. Eventually, you're going to have, for the last term, you're going to have 1 over z to the 8 all the way out here. But I think if you had to do this all the way out the long way, it would probably be just as tedious, or maybe more tedious than just doing the trig stuff that I rejected in the beginning. But there's a nice shortcut to it. What's going to happen is, think about we're going to be putting this whole thing back into the integral. And what's going to happen with each of these terms, like here, z to the 7 times 1 over z, this is going to become z to the 6th. So when we integrate, for every one of these terms, there's going to be, we're going from 0 to 8 pi, there's going to be some constant in front. Like here it's just, well, we can exclude this, but even with this, it's going to be like a 1, but then this is going to be like an 8. This is going to be 8 choose 2. So there's going to be some constant in front. And then we'll have this thing, which we'll write as z to the n for a second, but we're integrating with respect to x. So what I really want to do is put it back into x. So using our definition, this is going to be like e(i)nx. When we integrate it, we're going to get c e(i)nx over in evaluated from 0 to 8 pi. Well, we're going to have some constants. We'll just not worry too much about that. We plug in 8 pi. We have e(i)n 8 pi minus plug in 0. That's just 1. Well, for this thing, we have Euler's formula. We can use that here. e(i)n 8 pi, we can look at that as cosine, maybe let's clean it up a little bit. 8 pi n plus I sine 8 pi n. But we determined here that all of our exponents are going to be integers. The n value is going to be an integer. So what happens is integer times 8 pi even, it actually doesn't even matter if it's even. This part's going to 0. This part, again, integer, this part's going to 1. So this thing's a 1. So this thing's 0. And so we get a 0 in every case. So if I didn't know about the other methods, I might just put down a 0 here and think I'm done because every term's 0. There is one problem though. In the middle here, we're going to have one term that we need to deal with. This term when like our n value, or we'll have this 8 choose 4 term. And this is going to go with z to the 4 times 1 over z to the 4th. But z to the 4th times 1 over z to the 4th, this is just 1. So all we're left with here is just this constant, this 8 choose 4. So what we can do is actually, and this is the quick part, because if I wasn't doing this in a video, I would just really quickly get rid of all these terms and get right to this right here. All we want is this 8 choose 4. So let me clean this up, and then let's pretend we're starting the video right now, because you could very quickly get rid of all this stuff, and all you have here is a constant that we're integrating, and it's all going to come up front. So we're going to have 1 over 2 to the 8th, just this 8 choose 4, and we're integrating from 0 to 8 pi, we're just integrating 1. Do this out, what you have, you've got, this is the same thing as 8 factorial over 4 factorial over 4 factorial, 1 over 2 to the 8. When you integrate this, you get x, the 0 is nothing, you're just going to get an 8 pi here. Then simplify, expanding out 8 factorial, I'll write it as 8 times, I forgot a 7, 8 times 7 times 6 times 5 times 4 factorial. 8 pi, let me write this as 2 cubed. There's going to be a lot of 2's, so we're going to need to cancel 2's, like right here with the 2 to the 8th. Then we're going to have 4 factorial. Yeah, okay, let's write that as 4 times 3 times 2, and then times this 4 factorial. I can cancel 4 factorial here with this. 3 times 2 here is 6. I can cancel that here. This is 2 cubed. So 2 cubed times 2 cubed, we get 2 to the 6th times 35 pi. Over here, we've got 2 to the 8th times 4. Cancel 2 to the 6th with 6 of these, and we get 2 squared, 4 times 4. Final solution, 35 pi over 16. Method 2, we've got over here our formula for power reduction. This one is for when we have even n. We need the bounds to be 0 or integer multiples of pi over 2. We can go right to the formula on this. So for I sub 8, we're going to put this in terms of double factorials. So n minus 1, that's going to be 7 double factorial over 8 double factorial. The I sub 0 value is easy. That's just when n's 0. So when n's 0, this becomes 1. You're just integrating 1 from 0 to 8 pi. This is just going to be x from 0 to 8 pi. This is just going to be 8 pi. So we'll plug this right in here and we'll just simplify it. For the double factorials, if we start with an odd term, we get all odd terms. So it's going to be 7 times 5 times 3 times 1. We got an 8 pi on the end. This is going to be all even terms, 8 times 6 times 4 times 2. 4 times 2 is 8. I can cancel this here. 3 and 6, I can cancel this to a 2. Putting this together, 35 pi over 16, and that's it. Okay, method 3. This is also going to go pretty quick, but it's a little complicated in a video because we need to reduce the bound. For the Wallis integral, what it says is we need the upper bound to be pi over 2, lower bound to be 0. So we're basically done if we can get the bound to pi over 2, but we have to reduce it. We can do it out this way with these principles of the definite integral over here to the right. You could also do it from the graph. It's really the exact same thing either way, and this might seem more complicated, but it's just as fast once you're used to it because you just do this all in one step. But doing it out, we need to do these 2 checks here. We need to check f of x plus a, and this one is totally wrong. Sorry about that. This needs to be, it's a lot like King's principle where we add the bounds. So this needs to be f of 2a minus x right here. So actually we need to check this one first. For the NA value for this upper bound, that's our 8 pi. So we have n equal to 8. I should probably use something different. I don't want to confuse it with the n that we were using before here, but 8 times pi for the a value, so a is pi. So what we want to check is f of x plus pi. So that's just going to be, we're just checking f of cosine x plus pi. That's minus cosine x. But we're raising things to the 8th power. We're raising this to the 8th power. So this is going to be cosine 8 to the x. And that's the same thing as our f of x value we have right here. So this check works, and what it allows us to do is take the n off the bound, take the 8 off, and just bring it out front. So when we do that, let me just rewrite it to see what it looks like. Unfortunately, you can't use pi over 2 for the a value in this case, just because then it's the complementary angle formula and you get a sine, so it doesn't quite work. But then next we're on to the Queen's principle. Now where the 2a is going to be pi, so now what we need to check is just f of pi minus x. So that's going to be, in this case, cosine pi minus x, kind of the same thing as before. This is minus cosine x. But really, everything is to the 8th power, right? This is to the 8th power. So this is going to be cosine 8x, which is our f of x. So this check works. So what that allows us to do is we take the 2 out front of the integral, divide the upper bound in half. So if we pull a 2 off of this, what's going to happen? Now we've got 16. This becomes pi over 2 here. But now we're almost there because we can use the Wallis integral, which works the same way as the power reduction. This is the n value, so now we take that minus 1, so we end up with 7 double factorial over 8 double factorial times that value, pi over 2. I can cancel 2 here with this and get an 8. So let's see what we have. We've got 8 times 7 times 5 times 3 times pi. Just expand out the 8 double factorial, same as before. Cancel 8's here, cancel 3's here, multiply it out, and for the solution, we get just 35 pi over 16, and that's it. Okay, so there you go, 3 quick methods. Let me know what you like the best, or if you've got a 4th or 5th method that you like better. Okay, that's it for today. Thanks everyone for watching. Have a good day.